Sounds good. I guess I need lights too. And let's get started. Okay. Tomorrow is a big day. Every day is a big day. We're gonna learn some cool stuff, I hope. But before that, ooh, clear page. That's dangerous. But before that, let's do some administration, just like very light. You might have seen that the web page was updated with the lecture notes. We welcome all the feedback, either on the Slack channel or anywhere else. It's fine. We're curious about your questions that you may have and so on and so forth. And great thanks to Alex and Shivam, who were a great help to putting together these notes. And stay tuned for more of these notes to come. Assignment 0 was due a couple of days ago. We're going to release the solutions to assignment 0 today, hopefully, and we are going to release assignment 1 as well today. And that will be due in 2 weeks. And we're kind of staying on track, by the way. Like it seems that we can keep the schedule that I originally planned, so that's good. I don't know whether you guys have any questions. Before we start, related to this administrative things. Oh, project description should be coming soon too. Or the instructions of how to prepare the project. Next couple of days. Okay, let's start then. So today I want to talk about 3 things. It always have to be 3 things. So the very first block today should be some recap. Yeah, my little thing is overheating and I'm doing all kind of silly things. Some recap, and then we need to talk more about value iteration and how to use value iteration to come up with an approximately optimal policy. So it's like solve this computational question. So we want this policy to be, almost as good as the best that we could get with some positive epsilon. And the question will be how expensive is this computation? So that's the first block. The second block, we'll talk about some algorithm that's called policy iteration. And this is a very curious algorithm. It is always at least as fast in terms of its iteration complexity as value iteration. But it has the property that in these MDPs, it can terminate and find an optimal policy after finitely many iterations, after up to log factors SA over 1 minus gamma iterations. This algorithm can be done and just like output an optimal policy. It doesn't need to do approximations or anything like that. So this will be the main new part. So this is the new part. And then this makes us ask questions about, like, what's the inherent computational complexity of finding optimal policies or approximately optimal policies? What is the computational complexity of planning? In finite MDPs. That should just be a discussion. Nothing really technical there. There should be a lower bound. We always want to know, but there is some room for improvement for algorithms. So you come up with some algorithm and then you prove a bound. Oh, this is how good it is. Like, how do you know that this is not a crappy algorithm? Nah, you prove a lower bound that shows that in a way it can be improved, and then you are happy. Or you prove a lower bound, and then there is a gap between the lower and upper bound, and then you must be wondering about whether there is some room for improvement. All right, so these are the blocks. So let's start with the first block. So MDPs, it's just this 5 tuple. We have states, actions, transitions, rewards, and we are discounting. Okay. And then we have policies, and then the policies could be either general, or they could be just memoryless. So the memoryless policies are good because they have a compact description, and they just assign a probability distribution to every state. The general policies are good because potentially they are much more powerful than the memoryless policies. Later on, when we're going to talk about learning and whatnot, then these general policies, their class is going to be extended a little bit more. If you don't know the MDP and you're interacting with the MDP, then you want to use all the information that you received so far to come up with a decision about what action to take next. So that takes the form of a general policy, but the generalization to what we are considering now is only that in general you don't know the reward. So you would need to put the reward also into the information that you're basing your decision on what action to take. So the histories would include the reward. Here, the reward is not included in the history because we're talking about planning problems where we're just like wondering about whether you could do better if you allowed policies to use the history, and the reward doesn't really matter, right? Because the reward is just given to this policy. So the best policy, given all the information, it may or may not use past information, and that's the question we are after, and that's the fundamental theorem that I mentioned in the last lecture. That is what that result clarifies. So the fundamental theorem again. Says two things. So you recall the definition of V star, that was the optimal value function. So the first is that if you have a policy pi, which is a memoryless policy, which is greedy with respect to V star,
are we still denoting memoryless policies by pi ml, or?
We always use interchangeably pi, both for memoryless and general policies. If I have to use some extra notation, I will. Yeah. So P in this case is memoryless because it's a greedy policy, and if you talk about a greedy policy, then by definition it's a memoryless policy. So the meaning of this in terms of this operator language is that T of pi v star is equal to T of v star. And there is a lot of baggage here, right? So what the heck is T of pi? So T of pi v is this operator that takes the reward vector, immediate reward vector underlying this policy pi, and adds to it the prediction of what's going to happen in the future if you follow pi, and after you follow it for one step, you incur for all the future values, the values that are pegged up in this value function v, right? So that's T of pi. And last time I didn't introduce this, but you can introduce this T of A, and then sometimes I like to do this. This is the same as this T of pi, except that it's for the policy that takes action A deterministically in every state. And with this, the T operator is just this operator that you maximize over the actions of whatever T of A applied to V returns. So that's the one-step look ahead, one-step BAM on optimality look ahead. So these are these operators. And so the greediness just means that T of pi is equal, T of pi applied to V star is equal to T V star. That's equivalent to the definition of greediness. So that means that the policy with probability 1 only takes actions which are maximizing the one-step BAM on look ahead under V star. And so returning to the first part of the theorem, this is about the case when you take a greedy policy with respect to V star, and then you find out that, lucky for us, this is an optimal policy. So its value function is going to agree with the optimal value function. The second part of the theorem just says that the optimal value function happens to be a fixed point of the BAM on optimality operator. All right. So this is the theorem. Any questions so far? Doing well?
Just quickly clarifying, the thing you've written in a box is the assumption of the theorem, right? The greediness part?
Oh, that's just like expanding on the assumption and expanding on the definition. Yeah. So the greediness is like what's in the box is the definition of greediness. You can take that for the definition of greediness. It's equivalent to the definition of greediness. So
thank you.
All right. And then the last time I was saying that, okay, this theorem is has, like, there are two underlying parts in the proof. So first, if we happen to define the optimal value function just for policies which are memoryless, so we define this alternate optimal value function, then the whole theorem would be easy to prove this for this new value function. So part one, replace V star with V tilde star, prove the theorem. And then part two is just to show that, well, you can do this without losing anything, because V star is actually V tilde star. And the last time I kind of wrote the proof for this part two, and it's also part of the lecture notes. And now I just want to show how the proof for part one works. Okay. So the last time we already saw that V star is equal to V tilde star. So it's sufficient to prove that if pi is greedy, with respect to V tilde star, then it follows that V pi is equal to V tilde star. Okay, so this is what we want to show. How do we show it? Well, let's take all right. So the proof goes through by first noting that if you take any of these policies, any policy, then V pi is smaller than or equal to V tilde star. So that's automatic by the definition of V tilde star, because pi is also a memoryless policy. So it remains to be shown, so this is a question, whether we can upper bound V tilde star with V pi. Right, so that seems tricky, right? Like now we need to show that this policy which is greedy is actually going to do better in a way than any other memoryless policy. The idea is to bring in the optimal value function, or the Bellman optimality operator first. So we want an upper bound on V tilde star, and our best chance is to maybe show that this is a guess, that this may hold. So perhaps this holds. Okay. Well, we don't know whether this holds yet, right? So let's see whether we can prove this. What can we use for this? Well, if we show that for any policy pi, which is memoryless, V pi is smaller than or equal to T of V tilde star, will be done. Because we can just take the supreme over all possible such policies, and on the left-hand side, you will see V tilde star, right? So taking the sup over all pi in ML, from this, it follows that V tilde star is indeed less than or equal to T applied to V tilde star. So this would be good, but no, we don't know whether this holds. Okay, still don't know that. But, okay, so let's take any policy pi. So P, be a memoryless policy. What do we know? Well, we know that V pi is equal to T of, and I was writing this index, I think maybe in the, like the upper index or lower index. I'm going to put it low now. Hopefully that's not too confusing. We knew that V pi is a fixed point of this operator T of pi. We also know that, well, T of pi is just this operator that in the one-step Bellman look ahead, make some choices for the actions, like put some arbitrary probability distribution over the actions, and then averages over all those actions. And if you're maximizing, then you can only get something better than that, right? So the Bellman optimality operator, on the other hand, has a maximum over the actions. This is just a compact notation. This means that every state this happens. And if you write out, it's obvious that this happens. Okay? And we also know that V of pi, by definition, is smaller than v tilde star. So these operators, T of pi and T, have what is called monotonicity property. So if you apply T of pi on both sides, it's not hard to convince yourself. Well, what is T of pi? It's like add the reward, multiply with the stochastic matrix, the discount factor, do these things, right? Well, actually multiply with the stochastic matrix. That keeps the inequality, right? Because stochastic matrices keep this inequality, right? So they are monotone. And then multiply by gamma, add the reward vector underlying pi. All of these keep the inequality. So as a result of this, we see that T of pi of V pi is also smaller than T of pi of V tilde star. All right. And all right. So I don't need this. This was just distraction. Well, I could have done it differently, like apply T, but then I changed my mind and I said, okay, let's apply T of pi, because it's easier to argue that T of pi is monotone than that T is monotone, but it's basically the same argument. T is also monotone. All right. So now let's chain all these inequalities, and then, oh yeah, like at the end, we still have that. If you apply T of pi to any function, and you apply T to any function, the same function, then you get something bigger, because T is maximizing. You get something pointwise bigger. So this inequality also holds. If you chain together all the inequalities, then you find that V of pi is smaller than or equal to T of V tilde star, and then we're done, right? So this is what we set out to do, and then you can just take the supremum, and then you find that V tilde star is smaller than or equal to T V tilde star. The reason we are going through this is because this is a very typical argument that people use in all kind of proofs that we're going to do. We're going to use arguments like this a lot, like monotonicity of these operators comes up a lot. And you're just chaining these elementary inequalities and apply fixed point results. Okay, so the next thing is indeed to apply fixed point results. So remember that we set out to prove that this holds for the policy which is greedy with respect to V tilde star. And so far we got as far as showing that we have at least an upper bound, like we can take off if we apply T to V tilde star. So now recall that if pi is greedy with respect to V tilde star, so take pi to be greedy with respect to V tilde star, then that means that T of pi applied to V tilde star is equal to T applied to V tilde star. Well, and we just proved that this is at least as large as V tilde star. Okay. Let me make this nicer. Right? So we see that T pi, this operator applied to V tilde star, gives us some function that is at least as large as V tilde star. This is hopeful, right? What do I do next? Any ideas? Remember that I want to prove that V of pi, the value function of pi, is also bigger than this V tilde star. So we play the same game. Like we learned that this T of pi is monotone. What about applying T of pi on both sides? Right? So that keeps the inequality. So apply T of pi on both sides. Then you get that T of pi applied twice, which I denote by T of pi squared, applied to V star, is at least as large as T of pi applied to V tilde star. But we have this previous inequality that says that T of pi applied to V tilde star is at least as large as V tilde star, so chain with that. So we get that T of pi squared V tilde star is at least as large as V tilde squared. So now I can continue, right? Like I can do the same, do it k times, and I get that T of pi to the power of k. So T of pi applied k times to V tilde star is at least as large as V tilde star. And now recall that T of pi is gamma contraction max norm, or max norm space is complete. Therefore, by Bonox fixed point theorem, T of pi to the k applied to any function whatsoever converges to the fixed point of T of pi. And earlier we concluded that V of pi is the fixed point of T of pi. So this converges as k goes to infinity to V of pi. And so basically taking the limit of both sides as k goes to infinity, we can conclude that V of pi is at least as large as V tilde star, right? The limit is also going to keep the inequality. This is basic property stuff. Yes. Okay, so that finishes the proof, right? Because now we have this. And since we already had this from this two, it follows that they are equal, and we are done with part one. Okay. So that wasn't too difficult. It just had a bunch of steps. The way I remember is by remembering that this is kind of the key to show, because everything else is kind of automatic. That's a useful inequality to know anyways. And then once you know that V tilde star is equal to, okay, yeah, like, so in, once you know that V tilde star is equal to V star, then you also want to conclude that this holds for V star. And in fact, V star is a fixed point. Okay, so this is just QED for part one of the fundamental theorem. Part two of the fundamental theorem says that V star is actually a fixed point, right? So to see whether V star is a fixed point, well, we know that V star is equal to V tilde star. And then we already know that V tilde star is smaller than or equal to T of V tilde star, right? So it follows that V tilde star is smaller than or equal to T of V star. And to show that this fixed point holds, let's take this pi that is still greedy with respect to V star. So again, we have V of pi, and we know from part one that this is equal to V star, and this is equal to T of pi of V of pi because of the fixed point property. And we know that V of pi is equal to V star. So now use this to replace V of pi with V star. And now use that T of pi is greedy with respect to V star, so T of pi V star is equal to T of V star. And look at the left and the right-hand side, we have proved that V star is indeed equal to T of V star. Right? So just chain everything from here to there. V star is equal to T of V star. So now we can say that we proved this theorem. All right.
Chava, I have a question. On the previous page, what was the name for the last step? What was the name of the theorem that you used for the very last step, where you take K2?
Oh, there is no name for this term. Like this step that I'm circling here, when you're taking the limit.
Yeah, like how?
I mean, like if you, yeah, if a sequence converges and it's always in a closed interval, then the limit is going to be in the closed interval as well, right?
Okay. Okay.
Basically, this is what we are using. We're using for every state this. Right? So this is a property of real numbers. And the inequality, like, it's not a strict inequality. Like, that's lucky for us. If this inequality was strict, you couldn't conclude a strict inequality. You could only conclude a greater than equal, right? Like, so it's like AK for every K is bigger than some number A, then if AK converges, then its limit is also going to be bigger, right? Just a property of reals. Closeness under taking limits. This is the property that we also use in the Bonox fixed point theorem.
Yeah, I guess I was wondering the same thing that Matthew was asking, like, why does it go to V pi? Like when
this was the Bonox fixed point theorem? Okay, yeah, okay. So then, okay, I misunderstood the question. So Bonox fixed point theorem says that if you have a contraction over a complete norm space, then the fixed point of that contraction are uniquely defined. And if you're iterating the operator whose fixed point we are talking about on any vector of interest, and just keep going, iterate. So this is what's happening here. Like you apply the operator like any number of times, then this process converges, and the limit is the fixed point.
Okay.
So this converges to the fixed point of T of pi, and the fixed point of T of pi is V of pi. It's unique, like Bonox fixed point theorem also says that the fixed point is unique.
Okay.
Good. All right. Awesome. All right, so we are done with the fundamental theorem. So let's talk a little bit about value iteration before we switch gears.
Quick question, Chava.
Yes.
Does there have to be any conditions on T?
For?
I guess convergence for the fixed to be used in the Bonox fixed point theorem, if I'm understanding the question in the chat correctly.
Oh, like okay, the chat has a question.
Yeah.
Take a look. Conscience. All right, so Bonox fixed point theorem says that if you have a vector space on which you have a norm, and it's a complete vector space. So complete vector space kind of means that if you take Cauchy sequences, the Cauchy sequences are Cauchy in the sense that they are with respect to the norm. Then the limit of every Cauchy sequence is also in the space. So this is a basic property of Euclidean spaces. There all the norms are equivalent. So it doesn't matter which norm you're talking about over a Euclidean space. It's a complete normed vector space. Take any norm. So it happens to be true for the max norm as well. Then Monox fixed point theorem says that if you specialize it to Euclidean spaces, that if you take an operator, a map that maps this space to itself, and it's a contraction, that is like what's in the chat. It's L Lipschitz with a Lipschitz constant strictly smaller than 1, then the conclusions hold, which is that there's a unique fixed point, iterations converge to that at a geometric rate. Yeah. Right? And this is actually what we're going to need for the next topic, which is value iteration. So the fundamental theorem shows that if you knew V star, it would be awesome because you could just like gridify. That's a non-expensive operation, and you could read out from V star by one step bound look aheads and just like some trivial maximization over the actions. You could just read out an optimal policy from that. And the immediate question is, how do we get V star? So one very simple idea is not to quite get V star, but get something close to it, is to use what's known as value iteration. So in value iteration, you take some arbitrary initialization. But we usually take V naught to be just 0. And then you say that in the general case, the next iterate is computed by applying this Bellman operator on the previous iterate. Okay? So that's a finite computation, like you have to apply that for every action, the transitions, and like, and then do the discounting and the reward, do the maximization. You have to repeat this for every state. So there's a finite cost, this computation. This iteration has a finite cost. And if you do this, then again, Bonox theorem implies that V of k converges to V star exponentially fast. Right, and so here, since we choose V naught to be 0, here we just have the norm of V star. And for every policy, any policy, V of pi is at most 1 over 1 minus gamma, because we assume that the rewards are in 0, 1. And from this, it follows that if you take an infinite sum along any trajectory whatsoever, then this is between 1 over 1 minus gamma, which is, when you replace all of this with 1, that's the upper limit for the rewards. And then you get this geometric series, and you can just sum the geometric series. You get 1 over 1 minus gamma. And you can trivially lower bound the whole sum by replacing all the rewards by 0. So the value functions are always between 0 and 1 over 1 minus gamma if you have this normalization condition on the rewards. And therefore, the optimal value function, which is the supreme of these guys, is also in the same range. So in particular, its max norm cannot be larger than 1 over 1 minus gamma. So you can upper bound this by gamma to the power of k divided by 1 minus gamma. And then you might ask the question, okay, if I want epsilon accurate estimate of V star, so here the Vk should be epsilon close to V star, how big a k do I need? So fix some epsilon, solve for the k. And if you solve for the k, then you will see that you get this log 1 over epsilon 1 minus gamma divided by log 1 over gamma. Just reordering for k and then doing trivial calculations. And you can also easily show that you can make this inequality stricter by saying that, okay, k should actually be this large. And then this is what we like to call the Epsilon Horizon for this discounted problem, because this quantity is bigger than this quantity, where I just repeat what's in the numerator. In the numerator, I have this log 1 over gamma, and then this just holds by because log x is smaller than or equal to x minus 1 for x bigger than 0. I just like think about the graph of log, right? Just like you have this x minus 1 function, this linear function upper bounds log. Okay, so these many iterations are going to suffice for value iteration. And the good news is that the dependence on epsilon is very mild. So you have this log 1 over epsilon dependence. This is also known as geometric rate. This is also known here as geometric rate or linear rate. Like in optimization, people are a little bit more pessimistic and then just call this linear. This is a geometric or really fast rate. You're really not too sensitive to the desired accuracy. So we should be pretty happy about that. And every iteration costs you, like a fixed amount. Like the cost of this, the computational cost of this is like, for every state, you have to do a calculation that costs you as much as the number of states and actions, because you have to take some averages over next states for each of the actions. So that's like SA, and that's it. So altogether, this is a finite computation, but maybe, yeah, you can reorder this and then you can get it. But don't do that now. You can do that later. So, okay, this is okay, a good step, but let's say you stop after k steps and you get this V of k. And a V of k is, epsilon close to optimum, right? So if V of k minus V star in the max norm is smaller than epsilon, then that implies that V of k is at least as large as V star minus epsilon times the all one function, right? Like you subtract epsilon from all values, and then V of k is at least that large because they are epsilon close to each other. So let's say k is such that this holds. More generally, let's assume that you have some function v that you got somehow. You try to approximately compute v star, and this function satisfies this inequality. Okay, I can write a constant at the end or at the beginning. So this 1 is like this function that is constant 1 in every state. And what are we going to do with this? Like, our guarantee from the fundamental theorem was that if we computed v star, then we are golden. But we didn't compute v star, we computed something close to it. It would be very pessimistic, though, to believe that if you compute something really close to your idea, then you will get something really bad. So maybe that's not going to happen, but we have to see, right? So the question is, okay, at the end of the day, our goal is not to compute v star. Who cares about v star? Our goal is to compute a policy which is good, a near optimal policy. So how do we do this? How to get the policy? Any ideas? Greedify, yay, yes, let's greedify. Thank Matthew. So let's take pi to be greedy with respect to v. Right? Is pi a good policy? So we want to say that v of pi, its value function, is large. How do we show that? Well, we kind of like have some clue from the previous proofs. Whenever we're going to argue about v of pi, we kind of like end up arguing about t of pi, the underlying operator, and like that this operator on some functions is going to give you big values, then like some monotonicity or whatnot. Convergence gives you that v of pi is large. Same argument. So we have this inequality here. So what do we know? What do we do? So we know that v is at least as big as v star. So we can apply t of pi on both sides. So t of pi of v is at least as large as t of pi no, apply, this doesn't work. Like, okay, so this was a first idea. Let me write it out. And then this gives me a chance to talk about this, what happens here. So if you shift some input to this t of pi operator by a constant, what happens to it? Well, t of pi, t of pi applied to v plus a times all ones. Well, this is just r pi plus gamma p of pi, just using the definition, applied to v plus a times 1. And so this is just, okay. So p of pi is linear, so you can distribute it across these guys. A is just a constant, so A is a real. So you can pull that in front of p of pi. So from this you get, this is gamma times A. And p of pi applied to 1. You may recall the definition of p of pi. This is a stochastic matrix. So that means that all of its rows sum to 1. So that means that this is just 1. Okay? So what we get at the end of the day is that this whole thing is equal to t of pi applied to v, which is here, plus gamma times a1. So whatever constant you added to this value function, it comes out and gets multiplied with the gamma. Okay? So now this is kind of useful because, well, you can do the same with t. So if you do this with t, what happens? What are you guessing? Any guesses?
It's just TV.
Okay, TV, and then what happens to the rest?
Plus gamma alpha 1.
Yeah, well, the same thing happens. Even though t is a nonlinear operator, yeah, thank you for typing that up as well. even though t is a nonlinear operator because it has its max and all that, you can just pull out this thing from it. So that's awesome. Because we have this here. So here we see that, okay, we could continue and t pi v star would come out, but we don't know what t pi v star is, so that's kind of like dead end. So it's like, sorry, this doesn't work. But maybe not everything was in vain. So what's the second best chance? Well, we know that this holds. So maybe we can apply t on both sides of the first inequality, on both sides of this inequality, all right? So let's start. So v is greater than or equal to v star minus 1 epsilon. You know, like this proves sometimes the first idea doesn't work. That's okay. Apply t on both sides. You get t v greater than or equal to t of v star minus epsilon times 1. And then we know that we already calculated that this is like t of v star minus gamma epsilon 1. Okay. What do we know about t of v star? We know that just v star, right? So that was the fundamental theorem. Okay, so let's work on the other side of the inequality. So t of v, we chose to apply t on both sides because we also know that pi is greedy, so t of v is equal to t of pi v. So now this is a bit messy, so let's just write it out. So we get that t of pi of v is greater than or equal to v star minus gamma epsilon 1. Okay. So what next? Well, I guess it's better to write it this way. Well, doesn't matter. Okay, so are we making progress? Apply t on both sides multiple times. Yeah, so let's apply t on both sides. T or t of pi? If I apply t on both sides, yeah, maybe try t of pi, because if I apply t on both sides, and I know what happens on the right-hand side, but I don't really know what happens on the left-hand side. I don't really have the luxury to do anything with that. Okay. So maybe this is not quite great. Maybe I want to see V here. Can I put in V here? I can put in V. If it also holds that V star is greater than equal to V minus 1 epsilon. Okay. So I'm going to, like, we had this inequality here that V of k is close to V star. So that means that it's also lower and upper bounded, right? So now I can put in that T of pi V is greater than equal to V minus gamma plus 1 epsilon times 1, right? And now I can start to apply T pi, well, T on first sides, on both sides, and then what are we doing? Oh yeah, like T pi applied on both sides, and then T pi V equals to TV which is greater than equal to V star minus gamma epsilon 1. So if you apply T pi on both sides, then you get T pi squared V is greater than equal to T pi V minus gamma times 1 plus gamma epsilon 1, which is equal to TV minus the same thing. And TV was greater than V star minus gamma epsilon 1. So this is greater than V star minus whatever was here minus gamma epsilon 1. So altogether, like, we need to write down what we have. We have a gamma squared. We can pull out an epsilon from the whole thing. We have a gamma squared from here. We have a gamma from there. And we have a 1 times 1, right? Okay. So T pi squared V is greater than equal to V star minus epsilon times 1 plus gamma squared times 1. And then you can continue the same process, right? So here we had this inequality. And then we were doing some steps that introduced some additional things. And by induction, then you can show that T of P of K V is greater than V star minus epsilon times 1 plus gamma plus gamma to the power of k times 1. So every time this gets multiplied by a gamma, and then additional constant factor gets introduced, essentially. So take k goes to infinity. So this side converges to v of pi, and this side converges to epsilon over 1 minus gamma. So altogether, what we found is that, well, it's a little bit suspicious. Maybe I'm making some mistakes. It should be a factor of 2. But I'm not going to waste the time on trying to find where I slipped. Maybe I slipped somewhere with an epsilon. But altogether, what we find is that if pi is greedy with respect to v, where v is epsilon close to v star, then v pi is near optimal up to a factor of epsilon over 1 minus gamma. So lo and behold, it indeed does hold, does work that you just greedify. The suboptimality factor, though, gets multiplied by a 1 over 1 minus gamma. So that means that if we calculate the iteration complexity for value iteration, then we need to prepare for this and then pre-multiply the epsilon. So if we use the effective horizon notation, so recall that. The effective horizon was this quantity that guaranteed that if you run value iteration for at least this many iterations, then the error is going to be below epsilon. So you pre-inflate the error by a factor of 1 minus gamma, and then you find that your error is going to be 1 over epsilon 1 minus gamma. Sorry, epsilon is the other. There's no 1 over. It's going to be epsilon 1 minus gamma. And so you take pi of k, greedy, with respect to v of k. Then by this proposition, v of pi of k is at least as large as, copy this to here, like this. And so this cancels, so this is at least epsilon optimal. So the computation complexity is going to be something like this. So this is the iteration complexity, to be precise. The total computational complexity would be something like s squared a and this effective horizon, which has this log 1 over epsilon 1 minus gamma squared 1 minus gamma. So it has a log 1 over epsilon dependence, and it also has a 1 over 1 minus gamma dependence. And now we may be wondering about, okay, is this really necessary? It turns out that the answer was not known until very recently, about, I don't know, less than a decade ago. Inu Ye figured out a way to show that policy iteration, which is going to be an alternative algorithm, needs poly SA over 1 minus gamma iterations. And after this, it stops and outputs an optimal policy. So there is no epsilon, no approximations. It's pretty amazing. So it seems that the log 1 over epsilon is maybe not necessary. How does this work? So what's this magical policy iteration algorithm?
Chaba, before you move on, can I ask a question?
Yeah, sure.
So can you go to the previous page?
Sure.
Oh, sorry, one more. So this statement that you wrote on top left, is this always true? So for example, if VK is initialized to say something like 10, 10, 10, 10.
What do you mean by 10, 10, 10, 10? VK is the case iterate that you compute with value iteration. And if you want to reduce the error to V star, you better initialize V0 in the 0, 1 over 1 minus gamma interval. Anywhere you do that, it's okay. If you initialize outside of the interval, it might be reckless to do. Don't necessarily do that. If you have some better guess of what V star is, of course, you could use that in initialization of a iteration, reduce iteration complexity. But the worst case, you don't have any better guess. So you might as well initialize either 1 over 1 minus gamma, it doesn't matter, or like in the middle, or like at 0. It just should be in the range. And then the iteration complexity bounds that I was talking about are going to hold. Right, so policy iteration. So policy iteration is also an ancient algorithm. It works as follows. You choose a policy, memoryless policy, arbitrary. Again, if you had a guess about the optimal policy, for heaven's sake, please choose that. It may help you. But if don't, then you just choose any pi naught. And then K is going to be the iteration count. For each iteration count, the P of K plus 1 is going to be a new policy, such that this new policy is going to be greedy with respect to the value function of the previous policy. Okay, so that's the very compact way of describing what policy iteration is. So this means that the computation that you need to do in, I don't know, around K of this algorithm is as follows. You calculate the value function. How do we calculate the value function of a policy? How to do that? Give me some ideas.
to show you. I'm just going to do the
Just iterate t pi.
Sorry, I didn't get that. Like,
Iteratively apply t pi.
yeah, you could try to do that. So you could try to apply t of pi k I times on anything. I don't know, maybe the value function that you obtained in the previous time step or something like that. That would be an approximate calculation. But maybe you can do better. You can just like solve for this. If you expand this, you will see that this is just linear in the unknown v of pi k. So v of pi k is just identity minus gamma times p of pi k inverse applied to the immediate reward vector underlying this policy. So it applies to any memoryless policy. Just a matrix inverse. You can get it. The iterative calculation is just like an approximate way of solving this linear equation. And that would correspond to some iterative way of not even inverting the matrix, because you only are shooting for the solution. So it could actually be faster to do that than invert the matrix. But you can always invert the matrix. Yeah, question?
I was just going to say that this matrix is positive definite, so maybe you could just conjugate a method or something.
Sure. Is it positive definite or positive? I think it's a positive matrix.
Oh.
Okay. So you need to solve for v of pi k, and then once you solve for v of pi k, then you can just gridify, so that's simple. If you use matrix inversion, then, well, this is an S by S matrix. So it's going to cost you a little bit more than S squared, S to the power of 2.3 something, who knows, or S cubed if you're a little bit lazier. But it's a finite cost. So that's policy iteration. When do we stop? If you are resolving ties in a systematic fashion, that just means that you have an ordering over the actions. And whenever there is a tie between two actions, both of them are greedy, you always choose the index, the action with the lower index or something, the lower order. That comes first in this ordering. So resolving ties systematically, then you can stop as soon as you see that the policy didn't change. Okay, and then it's guaranteed that this returns an optimal policy, and then you have this iteration bound for it, which is a pretty amazing bound. So why does it work? At a very high level, first, you can show that this works because it's at least as fast as policy iteration. So what happens is that v of pi k minus v star is at most gamma to, like, the geometric rate of convergence still happens to be true. And the second is that you can prove that if you start this process, then after k star, which is roughly up to log factors SA divided by 1 minus gamma, after this many iterations, that exists in S naught, a state. Like, it doesn't matter how you initialize a policy. There exists a state such that for every k iteration count, which is larger than or equal to k star, the policy that is going to be selected by this algorithm at S naught is not going to choose the same action as pi naught, well, assuming pi naught is not optimal. So if you happen to choose pi naught to be optimal, then the algorithm will be done in one iteration. You evaluate it, and then pi naught doesn't change. Greedification is not going to move you from an optimal policy. It's stable. But if you happen to choose a suboptimal policy, then you can show that there will be some state such that none of the iterates after k star iterations are going to go back to the bad action. Like, this has to be a bad action because this process converges. None of the iterates are going to go back to this action anymore. Okay? So this works as elimination. So you can think about that here are my states and here are my actions. Like, I list all the actions. And initially, I don't know, like, pi naught chooses these actions. And then after k star iterations, one action here is going to be crossed out. After another k star iterations, well, after this happens, let's call the resulting policy pi of k star, and then continue applying the same result. We know that later on this action will never be chosen, but we can apply this second result also to pi of k star. So no, do k star more iterations of policy iterations starting from pi of k star. We know that there exists some other state such that, sorry, this was not good. The figure is misleading. All right, so I got confused about what my figure is saying. My figure wanted to say that here are the actions, and then pi naught happens to choose all these actions. And after k star iterations, one of the actions is crossed out and is not going to be chosen ever again. And then you can apply again this result, the second result, for the new policy that you get after k star iterations. And applying to this policy, well, this policy is choosing, like in each row, it's choosing some action. But what follows from this statement is that after k star iterations again, if you have this finite table, there will be another cross somewhere. We don't know where, somewhere. So how many times can I do the crossing? Well, at most S times A minus A times, right? Because at the end, for every state, there is an optimal action. So it's like, this is like the optimal actions are here. Like, we don't know where they are, but these will never be crossed, right? But these crosses appear every k star iteration. And the whole table has at most free spaces of SA minus A, right? Like, because A is reserved for the optimal actions. So after this many times k star iterations, right, this process has to stop. So I have to modify this. I think that this was just 1. Yeah. So after 1 over minus gamma steps roughly, this happens. Okay. The proof of the first part just relies on comparing what happens to policy iteration and value iteration. So you can prove that V of pi of k is at least as large as t applied to, sorry, this k plus 1, t applied to V of pi k. And of course, this is then at least as large as t applied k times to V of pi 0. And all of these are sandwiched between V star and this. And this converges to V star at the geometric rate, so this has to converge to, sorry, this has to converge to V star at the geometric rate as well. Oops. Okay. And so the whole proof here hinges upon showing this inequality, which follows by a few steps, just using the definitions. Connor asks whether we are only considering deterministic policies. Yes, like otherwise this table wouldn't make that much sense. So okay, yeah, like good point. Let these be deterministic policies because otherwise we go nuts, and like it's unnecessary to consider non-deterministic policies ever in this setting. Right. So there were some questions in the chat concerning S naught. So what's the truth about S naught? So the second statement again is that assuming that you start with a non-optimal policy, there exists state such that after k-star iterations, policy iteration will never ever choose again at that state the action that was chosen by the initial policy. Okay, and then that suffices to prove the result that we are interested in. Altogether, what happens? So the second part, the second statement, follows by a careful analysis, and I will just add it to the lecture notes. I think it's a very curious and nice analysis, but maybe it's less suitable for presenting it here. And altogether, what we conclude from this is that, well, with roughly, I don't know, S cube computation per iteration, because we have to invert that matrix, okay, maybe a little bit less than that. And then there is an S squared A part as well. So it's, you know, the max of these two, depending on how many actions you have per iteration. After SA over 1 minus gamma iterations, we find pi k such that this is an optimal policy. So there is no log 1 over epsilon, and there is a 1 over 1 minus gamma. So what's curious about this 1 over 1 minus gamma is that it keeps showing up everywhere, and we don't know whether it's real or not. It's kind of a delicate question. So if you want to do exact calculations, like exact optimal policy, no approximations, then maybe this is the result that you need to look at. Could we get away with less computation? The best lower bound I know of is Chen, and Mengdi Wang, unpublished paper in 2017. It's omega s squared a. And okay, I modified the proof a little bit, and maybe you like it. So you have s minus 2 states, where you have in each state a actions. And there are 2 choices. An action could either end up in heaven, or it could end up in hell. So heaven just means that there is only one action there, or like all the actions lead to the same state, and you get rewarded all the time. And hell means the same, except that there are no rewards. And the input in this case is given as a big table of, like, next state distributions. So given a state action pair, like here you have a state, and you have an action, and it can go this way or can go that way. And to know how to act optimally, you need to know whether this state action pair, like there will be only one action, let's say, at one state, which makes you go to heaven. And you need to figure out where that is. That means you know how to act optimally. So that means reading the whole table of S squared A transition probabilities. For every state and action pair, there is going to be a table, which will be filled with numbers. So here, there are the states listed from 1 to S. And I will give an arbitrary number to this heaven and the hell. So they appear somewhere in the middle of the table. But the table is mostly just boring, because pretty much everything goes to hell except for at one state, one action goes to heaven, and you need to find it. I know you know, I think, how to argue about that. This is going to take time that is linear in the size of this array, right? Like, you have to read this array. Like, otherwise you will not find out whether this state action pair is able to go to heaven or not. And you have to repeat this for all the state action pairs. This was on Holmberg's theorem, right? Like, essentially. The best chance is this randomized order algorithm, and it essentially requires S over 2 reads. So altogether, this gives you this lower bound. So now what's curious is that there is no 1 over 1 minus gamma, but I don't know. That's okay. I guess if there are bigger differences as well, because you have to multiply these guys. So at best, here with policy iteration, you get S cube A divided by 1 minus gamma. And then the lower bound is just S squared A. But now this is a very delicate situation, because if you have just few states, like a fixed number of states, then you could list all deterministic policies. And there are A to the S of them. And you can calculate, regardless of gamma, which policy is optimal. We know from the fundamental theorem that one of these policies is going to be optimal. So you can get a procedure whose running time is independent of 1 over 1 minus gamma. So for a few states, you could do it, and for fixed number of states, be polynomial in everything, regardless of the value of gamma. So it's really a question of like, how does the number of states compare to 1 over 1 minus gamma, which is sort of the planning horizon. So if you have fewer than that states, it's just like maybe then you just enumerate, and in the other case, you have to do all these other computations. But it's a delicate question of like, what is the exact polynomial dependence on S and A and 1 over 1 minus gamma. So all of these assume that you want to do exact calculation. If you're fine with inexact before that, for value iteration, we know that it's not good for exact calculation. So it can run indefinitely. You can just create a situation where there is almost a tie between going left and right, and then you initially go left, but you should go right, and then value iteration also geometrically fast, closing the gap between the look-ahead values of these two actions. The look-ahead value, the difference between the actual values can be so small that this takes arbitrary large amount of time. So value iteration is not good for this non-approximate calculation case. Does this mean this is a bad algorithm? No. I mean, like, for approximate calculations, okay, fine, you have this log 1 over epsilon, but it's not so bad. So maybe you want to do the approximate calculations. So all these kind of like raises the question, like, what is this really that you want, right? Like, what is the epsilon that you would be shooting for? Like, are you happy with this approximate calculations, or like, do you really need the exact calculation? I would say, like, we very rarely need exact calculation. We should be happy with approximate. But approximate calculation in terms of what? This epsilon was like an absolute error bound. And if you have, like tiny value differences, then maybe you want to do relative errors. And then that is a different question. To keep the relative errors small, that would be much harder. That's almost like doing exact calculations. But if you know that, like the optimal values are so and so big, and then compared to that, it's okay to lose a little bit. You have this absolute epsilon in mind of that, okay, 1 is a good number. Epsilon equals 1 because it's small compared to the maximum reward or maximum value that I could gain. Then the approximate calculations are fine. All right. So let me stop here, and next time we're going to continue talking more about approximate calculations. From this lower bound, you see in particular that the argument greatly relied on one part, on that you have to look at all the states in this set of S-2 possible states, because I required that you find the optimal policy, which means that you find an optimal action at every state. So just writing down the output means that you need to write at least S values, right? So then, of course, the computation is going to scale with S. So what happens if we leave that requirement, if we don't require that? After all, if you're doing planning, maybe someone's going to give you a state, point to that state and just ask the question, okay, what is a good action to take here? Can we save by that? Getting rid of this S dependence? The S dependence, the dependence on number of states is highly problematic, right? But this is lower bound. Like, no one can get away with doing less calculations if we are this demanding. So we'll need to change the problem. So next time we're going to talk about how to do that, what are the ways of doing that, and then see whether changing problem is going to allow us to have some algorithm whose running time is independent of the number of states. All right? Sorry, I'm a little bit over time. All right. Any questions in the chat or anywhere else?
I was just wondering if you're going to try and put the lecture notes up before next class. Or I guess not before next class, but before next Tuesday, maybe.
Yeah. Like I will try to be a little bit faster. So hopefully the lecture notes will be up before the weekend.
Oh, yeah, that's pretty fast. I look forward to that.
Yeah. Root for us.
Yeah.
We'll try. Okay. All right. Thank you.
Take care.